Assalamu alaikum everyone. This lecture is in continuation with the previous lecture. Okay, in our previous lecture we have discussed frequency response of amplifier, especially BJT. Okay, so we had a brief discussion about gain versus frequency response of the amplifiers. We said that gain versus frequency response, they look as I have shown in the diagram. Okay, there are three different types of gain versus frequency response. So we'll be extending or elaborating our lecture in context to RC coupled amplifiers. Okay. So in this lecture, we'll be discussing low frequency response and high frequency response of the BJT. Low frequency response and high frequency response of the BJT. Now, see, we know that for an amplifier, gain versus frequency response, it looks like this. This is the gain versus frequency response. This axis will mark you frequency F, okay, and then we have gain here on y-axis, which is sometimes shown as, say, if, for example, this is voltage gain. So this is the magnitude of gain, okay, magnitude of gain. And we have already seen that gain versus frequency response, it looks like something like this. There are three different regions of this gain versus frequency response. One is known as low frequency region. Okay, so suppose this is a line here which marks the cutoff frequencies. Okay, I'll tell you what are the cutoff frequencies. Now this in this gain versus frequency response, if we will see, this is the maximum gain. Okay, this is the maximum gain of the amplifier. This is the maximum gain of the amplifier, and we mark it by A max, or we can say AV max, because it is voltage gain, if for example. So this is the maximum voltage gain. These points, which are known as cutoff frequency points also, or half power frequency points, here the gain is 0.707 times the maximum gain. Okay, so here at this level we have 0.707 of the maximum gain, AV max, or we say it is root 1 by root 2 times AV max. Okay, 1 by root 2 times AV max. So the maximum gain from this gain versus frequency response, you can see that maximum gain is AV max. Okay, it is AV max, and you can see that if we decrease the frequency below certain cutoff frequency, say for example this is FLC or FL, which means lower cutoff frequency. Okay, lower cutoff frequency. This is F of H. F of H is nothing but higher cutoff frequency. Okay, what are cutoff frequencies? Cutoff frequencies on gain versus frequency plot, they are the points or the frequencies where the power of the amplifier reduces to 1 by 2 or half of the maximum power. Okay, therefore they are also known as, also called as, half power frequencies. Half power frequencies, half power frequencies. So we have two types of half power frequencies or cutoff frequencies. One is known as lower cutoff frequency, that is here. Another is higher cutoff frequency. Okay. So what happens at cutoff frequency? After cutoff frequency or higher cutoff frequency, the gain always reduces. Okay. So before lower cutoff frequency, the gain also reduces. Between these cutoff frequencies, the gain always remains constant. Okay. So the gain between these cutoff frequencies, the area is here. Okay. The area is here. The gain remains constant here. Therefore, this is known as mid band also. Okay. Mid band. Mid band. So what is mid band? Mid band of the amplifier is where frequency of the amplifier is constant and is equal to A max or AV max. In midband, the frequency of the amplifier, sorry, the gain of the amplifier is maximum. The gain of the amplifier is maximum. Okay. The gain of the amplifier is maximum and it is equal to AV max. Okay. Sometimes, so therefore, difference of, since FH is the higher cutoff frequency, it has the higher value. So higher value minus lower value, FH minus FL, is also known as bandwidth, bandwidth of the amplifier, bandwidth of amplifier. Okay. So bandwidth, if somebody will ask you what is the bandwidth, bandwidth is the range of frequencies basically for which an amplifier will provide you a constant gain. Okay. Bandwidth is the range of frequencies for which the amplifier will provide you a constant gain. How much gain it will provide you? It will offer you gain equal to AV max or maximum gain. So bandwidth is the range of frequencies for which an amplifier will offer a maximum gain. Okay. So bandwidth is range of frequencies for which an amplifier will offer a constant gain, which is equal to A max, maximum gain. Okay. And bandwidth is equal to FH minus FL, which is equal to higher cutoff frequency minus lower cutoff frequency. Okay. Suppose if for an amplifier f of h is equal to 200 kilohertz and f of l is equal to 50 kilohertz. Okay. Therefore, the bandwidth of the amplifier is 200 kilohertz minus 50 kilohertz, which is equal to 150 kilohertz. Okay. Kilohertz. So it is equal to 150 kilohertz. That is the bandwidth of the amplifier. Okay. Now see, from our gain versus frequency response, we can see that we have three different regions. One is known as lower cutoff region. Lower cutoff region. We have already discussed this in our, I think, previous lecture. Yes, we have lower frequency region, then we have mid frequency region, then we have higher frequency region. Okay. So in our gain versus frequency response, we have three different regions. Okay. So one is known as lower frequency region. The second one is known as mid frequency region or mid band. Okay. Mid frequency region. The third one is higher frequency region. Okay. Now see, we know that in mid-frequency region, the gain remains constant. The gain is equal to AV max, okay? It is equal to constant. It is equal to AV max. In mid-frequency region, the gain is always constant and it is equal to AV max. But what happens in lower frequency region and higher frequency region, the gain decreases. The gain decreases, okay? In lower frequency region and higher frequency region, the gain decreases. The gain decreases. Now see, the gain in lower frequency region decreases because of the coupling capacitors. Because of the coupling capacitors, we have seen in our amplifier, say for example, we have an amplifier like this, a BJT amplifier with fixed bias, something like this. So you have R1 here, you have R2 here, okay? R2 here, then we have, this is the base, this is collector. Say for example, this is RC here, and this is VCC here. You have RE here. Then we have a coupling capacitor at the output of the collector. This is collector, this is emitter, and this is base. Okay, so this is V output here. Similarly, we have a coupling capacitor at the input. Okay, so this is V input. This is also coupling capacitor. This is a coupling capacitor. So we have already seen the coupling capacitor. Okay, we have already seen the coupling capacitor in our previous lecture. And we also have a bypass capacitor here, which is CE. Okay, CE. So this is a complete amplifier. Now see, if you have here, this is an input here. Here you have a source here, input source, an AC source. This is B input. Now see, if the frequency will be very low, if the frequency will be very low, then, or if frequency will be very small, then the input will be DC. Okay, input will be DC. We have already seen here that if the frequency is very small, we discussed it in our previous lecture also, if the frequency is very small in AC signal, it nearly resembles the DC. It nearly resembles the DC. Now DCs, they are actually blocked by the coupling capacitor. They are blocked by the coupling capacitor. Therefore they will not be allowed to pass to the input or to the base. This is the reason why the gain in the low frequency region is small. Okay, you have a very small gain in you have a very small gain in the low frequency region in gain versus frequency plot, because the input signal is having a low frequency and it is not allowed to pass through the input. So there is no input or I can say that for a low frequency signal, for a low frequency signal, for a low frequency input signal, okay, the input impedance offered is very high, okay. So the amplifier offers a very high input impedance, because capacitor for high frequency signals, impedance, capacitive impedance is equal to 1 by omega c. Okay, 1 by j omega c. Xc is equal to 1 by j omega c. What is omega? Omega is frequency. Okay, omega is frequency. When omega will be nearly equal to 0, what will be x of c? X of c will be infinite. X of c will be infinite. When omega will be nearly equal to infinity, what will be x of c? X of c will be nearly 0. So for low frequency signals, when omega is very small or omega tends to equal to 0, yeah, frequency is small, x of c, the impedance, capacitive impedance offered by the circuit, okay, so capacitive impedance offered by the circuit is very large. So it is very difficult for the input signal to pass through and to be amplified by the amplifier. Since the signal is not amplified, or it is not allowed to pass to the amplifier, that is why you have a low gain. Okay, that is why we have a low gain here. That is why this region has low gain. So I can summarize here now. We can mention it here that we can mention here that In low frequency region, in low frequency region, the gain is small. Gain is small due to coupling capacitors. Okay, due to coupling capacitors. So this is the low frequency response of the amplifier. This is the low frequency response of the amplifier. The gain here is small because of the coupling capacitors. Because coupling capacitors, they offer a high impedance. They offer high impedance for low frequency signals. Okay, coupling capacitors offer a high impedance to low frequency signals. Hence, a lower gain. Okay, a lower gain. Hence, a lower gain. So, therefore, the gain also decreases. Okay, when the input will be completely having zero frequency, that is DC, then you know that the output will be also zero because there is no input there. Okay, the output will be also zero. There is no input. When frequency will be zero, the signal will be completely blocked by the coupling capacitor. It will not be allowed to pass to the base or to the amplifier. It will not be allowed to go to the amplifier, so therefore it will not be amplified, so there will be no output. So output will be zero, input will be zero, therefore the gain is zero. Okay, that is what you have here. Gain is zero somewhere here, so this is zero. So gain is very small. Okay, now for high frequency response, the gain after the higher cutoff frequency decreases. That is here. The gain in the high frequency region decreases because of parasitic capacitances of the network. Okay, parasitic capacitances of the network. Parasitic capacitances of the network and active devices. Okay, active devices and frequency dependence of gain of the transistor and frequency dependence of the gain of the transistor. Now see, our devices, our active devices, say if it is BJT or any other device, they are not ideal devices. They always have certain parasitics associated with them. For example, if we take a BJT, for example, you have NPN BJT, NPN BJT. This is emitter, this is base, and this is collector. You know that there is always a capacitance, parasitic capacitance between emitter and base. Okay, there is always a parasitic capacitance between base and collector. So these capacitances are parasitic. What is a parasitic capacitance? Which is an undesired capacitance, which we have not created intentionally. Okay, which we have not created intentionally. Which we have not created intentionally. So they are there because of the construction of the device, because of the nature of the device, and these capacitances, which are parasitic capacitance, they will always affect the operation. They will affect the operation. Okay, they will affect the operation of the device. These parasitic capacitances capacitances, they will affect the operation of the device. Okay, why they will affect the operation of the device? Because they introduce non-idealities in operation. Okay, So ideally, there should not be any parasitic capacitance present in the device. But once we fabricate the device, practically we realize the device, there are certain undesirable effects which will affect the operation because they will introduce some non-idealities in the operation. Okay. So that's why I say that because of these parasitic capacitances, the gain in the higher frequency region also decreases. Gain in the higher frequency region also decreases. In general, uh, the gain effects in the lower frequency region or in higher frequency region because of these capacitances, coupling capacitance or parasitic capacitances. Now see, let us see the power at cutoff frequencies. Okay, power at cutoff frequencies. Power at cutoff frequencies. Let us see the power at cutoff frequencies. Okay, all I will write down here. Let me write it down here. Power at cutoff frequencies. Power at cutoff frequencies. Power at cutoff frequencies. Now see the power of an amplifier, it is equal to V square, or any circuit, power of the circuit, it is equal to V square by R. Oh, okay, or it is equal to I square into R. Okay, so if it is equal to V square by R, we can write down output power is equal to V output square divided by R. Okay, V output square divided by R. But in our amplifier, we know V output, okay, V output divided by V input, it is equal to gain. It is equal to gain, okay, it is equal to gain. So if V output by V input is equal to gain, then what is V output equal to? V output is equal to AV times V input. AV times V input, okay. If we use this equation in equation 1 using in first, so we will have P output will be equal to AV V input divided by R whole square. Okay, whole square. Whole square. Now see, at half power frequencies, at half power frequencies, at half power frequencies, okay, this is the half power frequency line, this one. This is half power frequency line. At half power frequencies, the gain is AV by root 2, okay, AV max by root 2. At half power frequencies, we know that what is the gain? AV is equal to AV max divided by root 2. AV max divided by root 2. AV max divided by root 2. Okay. So it will be equal to, therefore, P output. Okay, I'll write down here. P output will be equal to AV max divided by root 2 into V input whole square. V input whole square. Okay. Then divided by R. Divided by R. That will be equal to AV max into V input whole square divided by 2R, because you have a root 2, once you square it, there will be only R will be left. R will be left. Okay. Now see, what is this portion? AV max V input square into V input whole square divided by R. Okay. This is actually here. This is P output. Okay. This is P output. This is P output. Or we can say this is maximum P output. P output maximum, because this is actually equal to AV max into V input whole square divided by R. Okay. Now we can write down then P output at half. This is actually at half power frequencies. Okay, half power frequencies. So at half power frequencies, P output will be equal to, it is equal to P output maximum divided by 2. Okay, divided by 2. So that is equal to half of the maximum power. Half of the maximum power. That is why these cutoff frequencies, they are also known as half power frequencies, because the power, output power at these cutoff frequencies, it is equal to half of the maximum power. Okay, half of the maximum power. So it is equal to half of the maximum power. Half of the maximum power. Okay, half of the maximum power. Now see, for our circuit that is shown here, okay, for an amplifier that is shown here, I'll draw this amplifier once again, then we'll discuss it. Let me draw this amplifier once more. Low frequency analysis. I'll write it down here. Low frequency analysis or board plot of an amplifier. So we had an amplifier like this. It was like a fixed or voltage divider biased amplifier. You have a emitter, we have a collector, we have RC here. Then we have VCC here. This is RC, this is R1, this is R2. Then we had RE also here. This is RE. We had CE here. And this was grounded. We had a coupling capacitor here. This is output. This is collector. This is emitter. Okay. And we have also a coupling capacitor here. And we had V input here. Okay. V input here. Whatever current will flow here due to the source or due to input, that will be called as I input. I input. And whatever impedance that will be seen by this source, okay, so this source will see a net input resistance of the entire amplifier, so that will be called as Z input. Z input is the input impedance of this amplifier. Okay, so we have an amplifier here. This is like this. So we have an amplifier like this. You have an entire amplifier. Its block diagram will be like this. This amplifier will have net input impedance which is equal to Zi, and it will have net output impedance which will be equal to Z output. Okay, Z output, which will be equal to Z output, which will be equal to Z output. So this is Z of I. Okay, this is Z of I. Z of I. Okay. Now see, if we will see for this amplifier, the input circuit, the input equivalent circuit, input equivalent circuit for this amplifier will be shown below. Okay, what is the input equivalent circuit? We had an input coupling capacitor that is equal to CC, okay, or CS, which is CC or CS, C of S, which is the series capacitor which is connected to the amplifier. Then we have net input impedance. Okay, so we have R1 and R2 in series. Instead of that, I will mark another resistance, which will be the net input impedance, R of I. Okay, then it goes to network. This is the input equivalent circuit of of the above amplifier. And we know that here between these 2 points, we connect a source voltage or source. Okay, we connect a source voltage or source. We connect a source voltage or source. Now see, for frequencies, for high frequencies, the CS or CS capacitor will be short circuited. It will be short circuited. So it will be connected to, it will be short circuited. CS will be short circuited. Okay. And for low frequencies, so for high frequencies, or I will say for very high frequencies, for frequencies which are very low or nearly equal to 0 hertz, what will be CS? CS will be open circuited. Okay, CS will be open circuited. So for high frequencies, the circuit, net equivalent circuit, this will be a short circuit. Okay, and then we have R of I, and then you have V output here. So this is V output to network. Okay, so we have V output then. So this is V of S, and you have a short circuit here. Okay, that is what is for high frequencies. For low frequencies, what will be the equivalent circuit? The equivalent circuit will be like this. So we have a source, then CS will be open circuited. Then we have input resistance. Okay, this is V output. This is source voltage, but this will be open circuited. Okay, this will be open circuit. This will be open circuit. Okay, this will be open circuit. So for high frequencies, what will be X of C? X of C for high frequencies, X of C will be equal to 1 by 2 pi Fc. Okay, X of C is 1 by 2 pi Fc. So when F is infinity, okay, when F is infinity, what will be X of C? X of C at F equal to infinity, or F tends to infinity, X of C will be nearly equal to 1 by 2 pi Fc. So F is infinity, so it will nearly go to 0 ohm. Okay, that is a short circuit. That is a short circuit. That is a short circuit. But when F is not infinity, when F is 0, so what is X of C? X of C for F when it tends to 0, what will be X of C? X of C will be 1 by 2 pi F of C. Okay, F is 0, so it is 1 by 2 pi. Instead of F, we'll write down 0, then you have C, so it will be equal to infinity ohms. Infinity ohms means open circuit. Okay, open circuit. So this is how the coupling capacitor will behave in low frequency or high frequency. In low frequency, it will behave as open circuit, and in high frequency, it will completely behave as a short circuit. It will completely behave as a short circuit. Okay. Now see, what is the output of this network? Output of this network. Okay. V output, if we'll determine the V output, see, this is a voltage divider network. This is a voltage divider network. Okay. This is a voltage divider network here. You have Vs, which is equal to V input. Vs is equal to V input. And then you have two capacitances, say for example, or two resistances or two impedances. One is Ri equal to R. Then you have another impedance is for CS. Say for example, it is X of C. Okay, it is X of C. So if we try to apply a voltage divider network rule, okay, the output of a voltage divider network would be V of output will be equal to R times V input divided by R plus X of C. Okay, so this is a voltage divider output. Voltage divider output. Okay, so what is V output of this network? V output of the input equivalent circuit. V output, please remember that V output it is equal to R times V in, which is actually source voltage, divided by R plus X of C. R plus X of C. Okay, R plus X of C. R plus X of C. Now see, uh, X of C is basically you have an imaginary part there. Okay, you have an imaginary part there. If we'll try to if we'll try to find the magnitude of output, because X of C is 1 by j omega c also. Okay? It is 1 by j omega c. So you have an imaginary part associated here. So if we will try to find out the magnitude of output will be equal to R times Vi, okay, divided by R square plus XC square whole root, okay, root of this thing. Why? Because if you have a number like A plus J beta, A plus JB, okay, it is equal to, for example, Y, then magnitude of Y, it is equal to root of A square plus B square. Okay, this is how we find out the magnitude. Similarly, you have X of C, it is 1 by J omega C, 1 by J omega C. Okay, so you have J there, that is that's an imaginary number. Okay, anyway, so we can find out the magnitude of the output, which will be equal to this thing, okay, so root of R square plus XC square. Now see, for special cases, R can be equal to X of C. So there will be certain point when we can make R equal to X of C. If R is equal to X of C, then what will be V output? V output magnitude, it will be equal to RVI divided by R square plus XC square root. Okay, so here X of C is equal to R square, or X of C is equal to RC. Okay, R, X of C is equal to R. For special cases, X of C is equal to R. So we can write down it under root R square. Instead of XC, we'll write down R square. XC square, we can write down RC square. Okay, so then it will be equal to RVI divided by twice R square root, so which will be equal to RVI divided by 2 root of 2 RVI divided by R times root of 2. Okay, now you have R in the numerator and you have R in the denominator, they get cancelled out. So the output, please remember, the output is equal to, now here it is equal to Vi divided by root 2. Vi divided by root 2. Vi divided by root 2. Okay, Vi divided by root 2. And what will be the gain? Gain, we know that gain AV is equal to V output divided by V input. Okay, so gain at this point, when XC will be equal to R, so gain when XC will be equal to R, it will be equal to V output by V input. What is V output? V output is V input by root 2. Okay, and then divided by, what is V input? V input is V input. Okay, you have V input at the top, you have V input at the bottom, then we will obtain 1 by root 2. 1 by root 2. 1 by root 2. Okay, so gain, or the voltage gain at a point when XC will be equal to R, it is equal to 0.707. Okay, so this point X, where XC is equal to R, this is known as cut-off frequency point. Cut-off frequency point. Okay, the point where Xc is equal to R, it is known as cutoff frequency point. Now you see that at cutoff frequency point, the gain is equal to 0.707. Okay, we have already seen it here from the graph. At cutoff point, the gain it is equal to 0.707 times the maximum gain. Okay, times the maximum gain. I'll stop here. I'll continue this lecture in my next lecture. I'll provide you further explanations about this. If you have any confusion, you can ask me or you can contact me. Thank you.